Folks, we're going to learn how to do proof by mathematical induction that involves inequalities. So we've got an example here. We're required to prove 1 plus x to the power n is greater than 1 plus nx squared, where we got n is an integer greater than 2 and x has all real values greater than 0. So we start off with our usual initial step. All of that's the same. In fact, the general steps are, of course, the same. So because n is the set of numbers, integers greater than 2, our initial step is proposition when n equals 3. So p of 3, and so we write our expression out for that, which would be 1 plus x all cubed is greater than 1 plus 3x plus 3x squared. Now, binomially expanding the left-hand side, we've got 1 cubed plus 3 times 1 squared times x (3x squared) and x cubed. Right hand side written there, and it's clearly the case that the left hand side is bigger because x is greater than 0, and the difference between this line and this line is x cubed. So it holds for the initial step. So the inductive hypothesis, we assume p of k is true, so we write out the proposition 1 plus x to the power k would be assumed to be bigger than 1 plus kx plus kx squared. So for when n equals k plus 1, doing the inductive step now, we look at the proposition, and that would be 1 plus x raised to the k plus 1 would have to be bigger than 1 times k plus 1 x plus k plus 1 x squared. So we're required to prove that. So that's, don't lose sight of that, that's really important, okay? So we've basically, I'm just going to call this to statement 1, and I'm going to call this statement 2 in case I want to refer back to them. And so the left hand side for this n equals k plus 1 step we have 1 plus x to the k plus 1. Now, using our index laws, would be 1 plus x to the power 1 times 1 plus x to the power k. So that's x. Rightio. So we've got now, we're going to refer back to from statement 1, which is the line for p of k, the inductive hypothesis. So from 1, and this is the key bit, alright? This is the key strategy which makes this a little bit different to some other inductive proofs. We've got the statement back up here. So whenever we see 1 plus x to the k, we know that it is bigger based on the assumption of 1 plus kx plus kx squared. So rewriting the line in a more creative way means that we're going to replace the 1 plus x to the k. Because it's an assumption, we use it, and I have to change something right here, right now. Do you know what it is? Yes, it's the inequality. It's bigger than. Okay. Another way of looking at this would be to say that 1 plus kx plus kx squared is smaller than 1 plus x to the k over here. And so this line going to that line, that has got a smaller value. So if this was equal to this, it's bigger than a smaller value. So 1 plus x to the k plus 1 is greater than that line we just wrote there, and which means it's greater than the expansion of all of that. And then we simplify everything, so we have 1 plus kx plus x plus 2 kx squared plus kx cubed. This last line might not be apparent first time you do one of these. You can see that I've grouped the x terms, or factorized the x terms and factorized the x squared terms, because I'm going to get a couple more of those sort of terms when we develop the right hand side. And through experience we get better at seeing these things. It might not be apparent first time you do it. So using statement number 2, which was for when n equals k plus 1, we see that same term here in use compared to the term at the beginning of the inductive step there. And it's clearly the case that if you see the matching green sections there, it's clearly the case that the term on the left of the inequality is greater than the term on the right, because everything else is identical except for this part here. And for the possible values for k and x, we have an important discovery. You see, back to the yellow again, we had to show that this here is greater than that there. We've shown that this here is greater than that there, but that there is greater than this here. So with a bit of direct logic, we can say that what we needed to show is indeed the case. So 1 plus k plus 1 outside of x plus, so saying that again, is greater than 1 plus k plus 1 x plus k plus 1 x outside of x squared, which is what we were required to prove. So we've shown that it works for, it's true for n equals k plus 1, assuming n equals k is true. Now the reason why, the mathematical reason, is since for k greater than 2 and x greater than 0, it's pretty easy to see that this 2k plus kx is greater than this k plus 1. Because 2k is greater than k plus 1 when you have those values there, and the kx is always going to be greater than 0 for those values. So yes, indeed, it has veracity, it works. So we've shown now, we just got to write our formal statement at the end. So proven by mathematical induction, since it's true for n equals 3, and when we assume, say, n equals k, it also holds for n equals k plus 1. And that's our proof. Inequalities.